Hi Nicole, this is for 5-2, and the problem is says that the bond length equal the internuclear distance is 0.1275 nanometers. All right, so that I'll just call that the R is 0.1275 nanometers. Eventually, we're going to need this in meters, so I'll just say right away that this is that many meters, since there are 1 times 10 to the minus 9th meters in 1 nanometer, and this is 0.1 nanometers, so it should be smaller than. All right, so that's right. Now we're going to need the R because we're talking about a rotating thing. So this is the H, this is the Cl, and it is rotating around 3 axes. This is one of the axes. Now, since it's rotating, we don't use the mass. We're going to use the moment of inertia. So moment of inertia is the reduced mass times the bond length squared. Okay. So what is the reduced mass? The reduced mass, like in chapter 3, is the mass of the first one times the mass of the second one divided by the mass of the first one plus the mass of the second one. So that is going to be 1.008 AMU times 34.97 AMU divided by the sum of those. So that'll be 35.978 AMU. But these AMUs will cancel. We need to change this AMU to kilograms. Now, a lot of people like to use 1.66 something or other times 10 to the minus 27th kilograms is 1 AMU. But I find that hard to remember, so that number comes from the fact that the mole of Avogadro's number is designed so that 6.022 times 10 to the 23rd grams, AMUs are in 1 gram. But we want kilograms. So I use 26 here instead of 23. So that is AMUs per kilogram. The AMUs will cancel. The kilograms will end up on top. So the reduced mass here is this times this divided by this divided by that. No, that's not right, sorry. This times this divided by, oops, sorry. This times this, oh wait, I need to press the AC button. All right, this times this divided by this, right? Yes, divided by 6.022 E26. Yes, that is correct. That is the reduced mass. So 1.627 times 10 to the minus 27 kilograms. Nice. We have a reduced mass. Now we can calculate the I. So the I will be equal to this times that squared. So whatever is in the calculator times 1.275 times 10 to the minus 10th squared. That is 2.645 times 10 to the minus 47. That's 2.645 times 10 to the minus 47th, and that's in units of kilograms meters squared. Now, from the Hamiltonian, from the Schrodinger equation for rotational energy, the Hamiltonian times the wave function equals the energy times the wave function. The Hamiltonian that we use here is the momentum operator squared, or something like that. But anyways, we end up with the energy eigenvalues of that equation equaling, with the quantum number that we call J instead of N, the energy eigenvalues equaling J plus 1 times h bar squared over 2I. And there are different ways to express this. Many textbooks use B tilde to indicate energy or to indicate frequency, and this is in units of inverse centimeters. And they do that because the spectroscopy machines give information in units of inverse centimeters. Well, I think that's why they do that. But since your textbook is asking for the answer in joules, we need to use just the energy, all right? So energy 1 is going to be with J equals 1. Energy 0 is going to be with J equals 0, right? So the delta E is going to be energy 1 minus energy 0. So that's going to be, if I put a 1 in here and a 1 in here, that's going to be 2. So that's going to be 2 h bar squared over 2I. These 2's will cancel out. Minus, now E0, if I put a 0 here, 0 times anything is 0, so it's just minus 0. So the delta E, the change in energy, is just h bar squared over I. All right, now h bar squared is h squared over 2 pi squared. All right, so that's h squared over 4 pi squared I down there, okay? So I'm going to do that on the calculator now. Remember, this, what I have here in the calculator is the I, so I am going to put this on the denominator by using the 1 over x button. Now I'm going to multiply this by h squared, 6.626 E34 minus squared, divided by 4, divided by pi squared. Okay, and this is what I get. This is the delta E that I get, this many joules. All right, now there's a little problem here. 4.205. So I have 4.205 times 10 to the minus 22 joules. This is not the answer that your book has, but I do not know why your book has an answer that is exactly twice this answer. Your book says 8.4 something times 10 to the minus 22. That's 2 times this answer. I do not know why your book wants it to be 2 times this answer. The 2's cancel. So if you can figure that out, please let me know. I don't see any place where it would be the case where there would be a factor of 2 multiplying this thing. All right, so anyways, that is how to get the delta E. Now, how would you get the wavelength? Well, you know that delta E equals h nu, right? And you know that C equals lambda nu, right? So we're going to solve for nu here and substitute the answer in there, and you're going to end up with delta E equals hc over lambda. So we're going to solve for lambda here to get the wavelength, right? So that's going to be lambda equals hc over the delta E. So I'm going to put hc over this delta E, right? So this is going to go on the bottom, and h and c are going to go, this is a c, h and c are going to go on top, right? So here I have this number, this is delta E, I put it on the bottom with the 1 over x button, times 6.626, 10 to the power of negative 34, times the speed of light, 300 million meters per second, and I get this many meters. I get 4.724 times 10 to the minus 4. So that equals 4.724 times 10 to the minus 4 meters. Now, that is exactly double what the answer is supposed to be, which is 2.36 times 10 to the minus 4. But I don't see any place where you could get that factor of 2. I tried to look in the literature to see what is the real wavelength for the first microwave energy transition on HCl. And I found that it is, well, one source says that it is about something about around 20 inverse centimeters. So around 20 inverse centimeters. That would be half of this number here. So I think I'm doing something wrong, but I don't know where. What I'm doing wrong is there's a factor of 2 that I'm not accounting for, but I don't know where to find that factor of 2. I will let you know if I figure it out.